Good afternoon. We are going to resume the explanation of what materials are. Well, first of all, some information. The slides and the text, so understanding material science, is on my web page on Unicam website. And I hope you are able to to trace it. Of course, you have just the slides I exposed during the first two lectures. I will put these ones later on tonight. And the book, which basically follows the course. Of course, the book, as I was saying last time, gets up to 2005. It's a book that was issued 15 years ago, and therefore you can easily imagine that there are some developments, because material science is a new, I would say, new, although it has a long history, but it is new in terms of formalization, and it is a multidisciplinary science involving chemistry, physics, engineering, and also biology in a sense, because you may imagine that materials are not only synthesized, as I was saying last time, but also come from nature. What are we going to say today? We are going to concentrate on the fact that materials, which were defined as being able to withstand a force, well, materials need to be characterized from a mechanical point of view. Mechanical characterization is the simplest one in a sense. Also, not only from a modeling point of view, but also from the operational point of view, in the sense that it's not only reasonably easy to make calculations about mechanical properties, which are the ones that give to the materials their qualification, because a material is classified as such, as I was saying, because it's able to withstand forces. So we need to measure these forces. We need to specify which kind of forces the material, then the object from which we produce from materials, combining different materials, joining different materials, we produce an object. Say we produce a car, we produce a bicycle, whatever, a house. And therefore we need to have an idea of the forces, not only the dimension of the forces, the level of forces in a sense, but also the type of forces. So from your physical point of view, you may imagine that a structure, as I am showing here, well, which is indicates some very simple things. Basically, I apply this kind of force, this force F, and of course the structure, which is the A, B, C, D, E, is a generic structure which doesn't belong to any object to start with, but it's useful to make calculation. I apply that force, and you can imagine easily, even if you don't know anything about material, that beam, that line will bend. That line will go down, which is an expression of the fact that the beam will bend. Will bend by an angle, some angles phi, and you can say that these points A, C, and E may be blocked, or in other sense may be not able to rotate, or may be able to rotate, which suggests different questions. If they are able to rotate, of course, we will have a moment there, and otherwise we are going to have only moments in other nodes like B and D, but A, C, and E will be completely blocked, like it is in this case. And basically, the A, C, and D points are going to be steady, are not going to move. Okay, let's move a step forward. We need to consider one fact that in physics, you consider ideal systems like this one. The reality is very different, but but in some cases, it is interesting to have ideal assumption, to make some assumptions, to make some models, because we want to make calculations, and then you see to see how far we are from models. Here we are not talking on any kind of materials. You may remember that last time we were talking about metals, polymer, and ceramics, or composites, so hybrids. Here, well, we don't have any particular material. What we can assume in this ideal mechanical system is that, well, this is very simple. I am not saying that to offend you, but there is something that we need to consider. First, we have the section of all these beams, of all these lines, it's constant. And that's a point which is not trivial again, because if it is not constant, of course we apply a force, but the effect might be different on different points if the section is not constant. Then we have another trickier question, is that the material is ideal. So we suppose, we don't know which kind of material we have, but we suppose that the material is ideal. Then we are going to define into this lecture what do we mean by ideal material. So let's go first to one more clarification. We have 5 types of forces in engineering terms. We have a tension force when we pull the material. We have a compression force when we push against the material. We have a bending force, a flexural force when we bend our material, and we have a torsion force if we apply a torque angle. Okay, these are 4 types of force which are simple forces, in the sense that in normal cases, if you have a complex structure, it's unlikely that it's just subjected to any of these forces, unless it's very simple. But even if you have a very simple structure like a rope is subject to tension because you tend a rope. Think of a wire that moves the lifts up and down, for example. In a building, you have lifts, and we have you can have actuators, but you can have also ropes, kind of steel ropes, and steel wires, but between the wires of your bigger rope, you have torsion. They are kept together by a torsion angle. And therefore, it's unlikely, even with simple structure, that just one of these forces applied. Usually, we have a combination of forces. Anyway, it is clear that some types of materials are better suited for some applications. For example, steel works better in tension. It's unlikely that you use steel in compression. You may in some cases, but it works usually in tension. Concrete works better into compression. Wood works very well in bending. And with ropes, we apply torsion in many cases. There are many natural materials which work well in torsion. Natural fibers, for example. Then you can have shear forces. Shear forces are forces which are usually quite negligible if the structure is quite large. For example, you have a concrete cube, and you may imagine that it can have some shear forces, but close to the edges, close to the angles. In general terms, this is negligible over the dimension of the cube. However, we have structures more and more that are used in a very thin form, in a very thin geometry. As materials engineers, we call that films. A film is usually less than half a millimeter thick. So it's more a question of microns than millimeters. In that case, shear becomes important. For example, plastic bags. Down the supermarket, most plastic bags are broken by shear because they are very thin and they are cut, but by some other packaging, say, would cut these bags and they fail by shear. Shear can be tensile. For example, if you pull and the adhesive layer becomes detached, you may have two layers which are attached, which are bonded by an adhesive layer. You may pull and the adhesive tend to tear, so it breaks by tension. Compressive. This is very usual in some practical cases. For example, in the case of layers covering, for example, cell phones, the tiny layers protecting layers covering cell phones screens may break by compression because they are compressed, they are squeezed. Or this is not to be confused with impact. We are going to deal with impact as well, but impact is some weight falling on it. Compression is a way pressing on it. It's different. Impact is dynamic. Compression is static. It squeezes. Then you have interlaminar. Interlaminar, you may know that in composites like fiberglass, like carbon fiber composites, or Kevlar fiber composites, or in wood when it's used in furniture, we have laminates. And laminates may get detached after a while, may get detached because they move and they usually the detachment is due to bending, especially if the area is quite small. If the area is quite small, they tend to be bent. It happens with the laminates, wood laminates, and they tend to be delaminated. They tend to fall down, to separate from each other. You may have found this in furniture, especially for example, in the kitchen. It's quite typical that it tend to detach. Also by the effect of water acting on the glue, and it makes detaching. Then you can have some other situations, some other forces which which are not a simple force, but they are important anyway. In some cases, for example, if you tend to to press against some small beam, if you have a beam which is compressed and it's quite short, matter of centimeters or less, and is quite short and thin, then it can break by a complex force, which is called buckling. Basically, you have the so-called elastic instability, in the sense that it's still elastic. You may remember that elastic means that it recovers completely the force after this is removed. But even if you remove the force, it tends to buckle, it tends to be unstable, and then to break in a kind of sort of flexural breaking. Okay, so what you could have realized is that we are talking about materials, and of course, since we applied forces, we need to be involved of the fact that applying a force over a certain limit brings to failure. And since this is more an experimental than a theoretical course, we need to be involved with the fact that as far as the forces are different, also the way of breakage into the material of failure is different as well. Then we can start testing therefore materials. This is steel. We can easily see and say that steel is the material closer to an elastic one and closer to an isotropic and closer to an homogeneous material, which are the three characteristics of a ideal material. I will come down to that later on, but anyway, steel is the closest to an ideal material. What happens when we do a tensile test on a steel sample? This is a steel sample. The typical shape for steel sample, it's a bar, which is done in a bar or a flat specimen, which is shaped in the form of a dog bone. And so we call them dog bone specimens. But apart from this, which is of course subject to no normatives and standards, how to carry out tests, what do we do? Basically, we take this sample, we put into grips, and we start to apply a force. By applying a force in moving one of the two grips. One of the two grips is connected to the engine, and therefore it moves. The other one is typically steady, fixed. The other one moves, and therefore it pulls the sample. It pulls the sample, and the sample is elastic. Well, these are photos which are shown during the time and evolution of the tensile test. The tensile test is the simplest one to perform. Because there is a reason. There is a reason for this simplicity. It's not just a question of technology. It's also a question that obtaining a pure tensile force, it's easier than obtaining, for example, a pure compression force, as I was showing buckling before, a pure flexural force, because there is always as you may remember by the previous slide, bending is the combination of a compression and tension. So compression and tension. So you have a half which is compressed and another half which is tended, which is pulled basically. And in the end, what happens is that not all the parts of the sample are bent with the same extent of force, even if you apply, when they say amount of force, even if you apply a force down your machine. Then after that, there are some other consideration to do, which are more specific on bending tests, and which I will do later on. But anyway, the tensile, please bear in mind that the tensile test is the simplest one to get when you want to get just a tensile force. Here we can be quite sure that basically all the force we apply is tension. Of course, we need that kind of shape to be sure of that. We need to have a not negligible section, otherwise we get involved into shear force, as I was saying. But if this is the shape, and we talk about centimeters of length, of grip length, the length between the grips, and millimeters or up to a centimeter or so, 1 centimeter, 2 centimeters of section, of diameter rather, I would say that tensile force is about 100% of the whole force applied. Okay, at least on the grips where we get the measurement. Okay, so it's elastic. Up to a point, it's elastic. Then the behavior changes, and this is important because it becomes rather plastic. So up to image 3, I would say if I discharge, if I take off the force, unload, if you want, and I come back to image 1, then I can start again and again and again. And I get basically to measuring some force up to the elastic limit. And for a number of times, a large number of times, I am able to repeat the force and the sample stays the same. This has a consequence that if I want to use steel proficiently, if I want to use well steel in my structure, I need to get to a load lower than the elastic limit. Because after that, what happens? The behavior becomes plastic. The plasticity can be for a longer time or for a shorter time, and this depends on the characteristics of steel, because there are a number of types of steel, of course. We can go into more details later on, but please be aware that not all types of steel behave like that. This steel is not particularly brittle. It's not particularly brittle. When we say brittle, in operational terms, brittle means that it breaks suddenly. This specimen doesn't break suddenly, but it shows some necking. Necking means that the section is reduced around the half, the mid of the specimen, of the grip length. And it becomes thinner and thinner until we get to failure. This wasn't brittle. The contrary, the opposite of brittle is ductile. This tends to be ductile, and we can see that from the fact that we have plasticity for quite a long time. And you may easily imagine, I can tell you that the distance of time between 3 and 7 is much more, the time span is much more from between 3 and 7 than between 1 and 3. So it carries on elongating for quite some time. It elongates. It's not able anymore to recover completely to the initial length after image 3. And it at a certain point, after some time and some elongation. So we are able to measure the force and the elongation, and something else as well, which I will detail. So this is ductile. This is a still sample which is ductile, and its way of breaking, if we look in section to the two half of the broken, into the two broken parts, we can see that we find a cup and cone, we call it like that, to show that it is ductile. So ductile means that it carries on elongating and of course deforming, and also squeezing, because so we have this necking, and so the section is more reduced for quite some time. Okay, so which number we get from the tensile test? We get from the law, Robert Hooke's law. As I was saying last time, also Leonardo tried this, but with wood it was difficult, because with wood it was doing a tensile, not a tensile, but a flexural test, Leonardo, on wood, because it's not very easy to do a tensile test on wood, because it tends to delaminate. The different parts of wood tend to open, and we don't want that, because in the end we don't get any tensile information. It was doing flexural test, and flexural is not that easy to understand that there is a kind of linearity. It's not completely linear in wood. You don't have a complete linearity between the stress, I mean by stress applied force divided by the section, and the epsilon, which is the strain. For some reason, well, I will add that for some reason I didn't put strain again. Anyway, I will write it again. Okay, this is strain. So epsilon is strain. Anyway, you will find in the final slides, because it's my habit to have first the lecture and then to eventually to correct the slides if there are some mistakes, and there are always some mistakes, as you can see. Anyway, here it's missing, you miss strain, and the ratio between stress and strain, it's the elastic or Young's modulus, the modulus, which was discovered by Young, and here we are at the beginning of the 19th century, basically. There is this linearity between the stress and the strain. If the material is elastic, well, of course, you haven't, what you have seen last time, in the previous slide, wasn't a material like the one I'm showing here, because if the material was like that, it would have broken at 0.3. So, and it would have been brittle, because it would have broken suddenly, because in other words, if until the materials stay elastic, we don't have any warning of the fact that it will break. And therefore, if we don't have any warning, that means that it's going to be brittle, it's going to be sudden, the breakage. Okay, so we have a purely elastic behavior. This is typical, for example, in ceramic materials. You often find that, something like that. Some metals are sufficiently hard, and you get this kind of, even some types of steel, some types of ferritic steel, for example, you can get a failure which is brittle. Okay, it is important to remember one thing, that the forces determine also the, I'm showing here springs because forces determine also the geometry you want to give to the object. And for example, we have springs. You may recognize some of these springs. You may have, for example, in some simple objects you have at home. For example, pegs have a torsion spring, a typical torsion spring. And the ball pen have got the flexural springs. This is for seat. This is the most typical one, the compression spring. Even if you have some the end of the if you have the end of the travel end of your, for example, even a lift when it gets to the end, you find a big compression spring to compress it, which doesn't allow the lift to go further down. Okay, I'm saying about spring because don't forget that we always talk a little bit about history of material science, and Robert Hooke, when he was the, developing his law, and he was starting to investigate about how to do tensile tests, and of course the shape of the samples and so on, the geometry of the sample, the accuracy of the measurement, and etc. He didn't have any electronics, so basically he had to apply some weight in order to understand what was the force. That was that period. In that period, there was some development in another field, which was the one of springs for clocks. Clocks were developed at the beginning of the 18th century, end of the 17th, beginning of 18th century. And in fact, there were a number of springs to make more effective the clock working, because there was a connection between the kind of force you have to give to the spring and the geometry of the whole clock. They tended to be compression springs, but there have been also some tension springs and other, and also some flexural springs. So there was an interesting correlation between springs for clocks and the forces applied. You can have some compression springs, not just in a cylindrical way, but also in some other kind of structure, which were allowed to move in different way and to stop the device, whatever device. Now we are thinking of the lift, but compression spring is the spring that stops your system to go further. They don't allow it to go further. So, and this means that in some cases there would have been the need for modulation of compressive force, and therefore different geometries, etc. Okay, having said that, how is a tensile? Let's come back a little bit to what a tensile test system is. So basically, we understood that there are grips. Grips stop in a firm way your sample. Your sample is pulled by the fact that one of the heads is movable because it's connected to the engine, and as I was saying, the other is not. So it's firmly kept by the grips, which is not always obvious, not for all materials. And then you start pulling. Here you can see the necking. Different types of steel. You can easily understand, for example, that the first one, the left ones, elongated a little bit more than the other ones. You can see that it's probably around a little bit less than the double. Probably it elongated 1.5 times the other one. And this gives you the idea that there are, as I was saying, there are different levels of necking. necking can go even to a point. We can even have necking up to a section which is almost invisible. In the case of rubber, for example, some types of rubber, you can get a necking up to a section which is question of microns. Even if it's started as millimeters, then necking is very thin. You get to a very thin section. Necking is very pronounced, and in reality, you have a very, very high elongation, which you don't have with steel. With steel, you may have 10–15% of elongation. With rubber, you may get to 700% elongation. So if you started with a sample which was long 1, and the end, your sample was long 8. So this gives you a measure of an idea of plasticity. Of course, there are, with respect to the Hooke's times, we have more modern ways of measuring elongation, because the force it's quite easy to measure. The elongation it's less easy to measure, because you may be confident on the fact that it stays straight, and therefore you are able to measure the elongation in just by measuring on your scale here, on your on your measuring system here. Just but in other cases you are not able to measure by the scale here, but you need to consider that possibly it doesn't stay straight, and so it's better, and also that the elongation is not constant. And so you may have some further systems which give you a more accurate measurement, like the extensometer, which are a kind of two rings which are put at different places and give you the difference time by time, second by second, I would say. All the strain gauges, which measure the elongation in different points of your sample, based on the resistance, on the resistivity. You may know that the resistance, the electrical resistance, depends on the may have a relation with the variation of length. So you have this wire which changes into resistance, and of course what you measure is basically the voltage. Basically, you measure the voltage because you know the intensity of current, and you measure the voltage on your strain gauges. Whilst the extensometer is a mechanical measurement. Anyway, apart from all these details, it's important to remember the fact that tensile tests is the first test which is done on the majority of materials, apart from concrete and on wood, or concrete, which tends to be measured by compression test, and wood, which tends to be measured by flexural test. We'll give more details on these tests later on. But also, for example, in plastics and composites, usually perform a tensile test, and even on rubber. Okay. After that, we were talking about the failure types. Failure types might have a different shape, a different geometry, and there are some aspects that we need to consider. This is to the very left, we have a ductile fracture. It's an aircraft bolt. It's an aircraft bolt at the very center. It was broken at the very center. You may consider that structures like aircrafts, so very structural, systems which are subjected to forces and moments which are very at very high level and for very long times, and which undergo service which might be very long, which might last for years. um, have usually a number of junction elements, joining elements like bolts, which is much more than needed. If they, for example, well, if they need 100 volts to be safe, just to be safe to carry on the load which is needed, or to join the two parts in a safe way, you put the double or the triple. And so in most cases, you are not very worried about the fact that one voltage is broken. Although the paper from which I took that was quite frightening. It was the title of the paper was "Why Aircraft Failed." But anyway, in reality, you can bear the fact that a bolt is broken and need to be replaced. Was ductile. This was ductile because you see that you may imagine that you had the necking. This was under the microscope. You may imagine this is a section, and you may imagine that it had the necking which was traveling around for quite some time during the tensile breakage. So it was ductile, this failure, because you had internal deformation. In other cases, you may have a brittle fracture. For example, you have brittle fracture. How brittle fracture takes place? It is sudden. It is sudden, but we have a crack. We have a crack, which in most cases, in a crack defect, which in most cases in steel we don't see. It's very hard to see cracks in steel. Especially, it's very difficult to see which kind of crack. You may see some scratches on steel, but it's very difficult to say which of these scratches would lead to sudden failure. Sudden failure, might be a problem, and you can see that it is sudden because the surface it's quite smooth. It's quite smooth. It's not so complicated. It's not so thin like it was for the ductile fracture. In other cases, an important phenomenon which is studied a lot in engineering is fatigue. Fatigue means that you subject the material to a number of cycles. What do we mean by cycles? Cycles means times the material is loaded and unloaded. Because this was very difficult to understand at the beginning, because until the beginning of the 20th century, we didn't know much about fatigue. We did suppose one thing which wasn't always true. So that if we load a material below the elastic limit, then we are safe, we are okay. This is not true. This is not always true, because we can load the material below the elastic limit for a large number of times, but at a certain point, you may have a kind of fatigue failure, which is sudden, but is not due to the fact that the defect explodes at a certain point and progresses very quickly at a certain point, but is due to the fact that the defect is growing slowly, but at a certain point it gives you failure, which again is sudden, but it doesn't occur in a short time, but it occurs after a long time of loading and unloading. But the main difference is that fatigue fracture is below the elastic limit, so it's much more worrying. It's just because there is a wear, because the material has been loaded for many times, and this is much more worried than brittle fracture, because brittle fracture in most cases it's at the elastic limit or even slightly over the elastic limit. and by the effect of propagation of a crack, but um, at a considerable load. Fatigue fracture may even happen at low load. Fatigue fracture it is very interesting because it led to a number of studies of on glass, for example, the fracture of glass. Glass was redeveloped as a material. Now we have layered glass and tempered glass, which allow to be protected by fatigue fracture. Fatigue fracture in glass had the consequences quite important consequences. The studies of on fatigue fracture in glass, so sudden after a number of cycles, but even at low load. It was important because this doesn't always mean that the fatigue fracture means that the object is old. Fatigue fracture may even happen if the object is quite new, but it has been loaded a number of times, even very quickly. To make you an example, which we will talk of that later on, but an example which probably makes you clear what I mean is that, for example, the studies on glass fatigue fracture started from the sinking of the Titanic in 1912. And here the reason for sinking the Titanic was the explosion of the ship windows, because they were loaded with water by the pressure of water a high number of times, even if in a few minutes or so. And even if there were not visible cracks, there were not visible cracks, but they were able to explode because fatigue was doing this kind of produce this kind of vibration, which you can see, and this kind of rings. Fatigue is recognizable by this kind of rings, which give you the idea of propagation, very fast propagation of the crack, but at very low load. So it's not comparable with proper rooted fracture. We'll talk of that later on anyway. So here we are back to our steel sample. This is basically what happens if if we come back to our sample, you can see that the curve you will find from this sample is about like that, something like that. So you will have an elastic limit, some plastic deformation, then necking, and at a certain point, so you will have some elastic deformation, some plastic deformation, not recoverable, but the stress is able to go more, and then failure. Then failure at a certain point. You may have the idea that the stress remains about the same, but attention, the stress remains about the same, but in practice, this is the effect of the fact that the section is reduced more and more. So in practice, you apply a higher force on a section which is smaller and smaller, and therefore you get to failure. In the end, you get to failure. You have a kind of collapse. You get to failure. Okay, these are some. As I was saying, the main question is that the ductile fracture means that you have this kind of tips. You have this kind of ductile tips. You have some shear force in the end. In the very end, you have some shear force, some breakage by shear, and you have these tips, which are connected with ductile behavior. Whilst if you have a brittle behavior, then you have some breakage, which is connected to the fact that there are cracks. That cracks tend to merge between them. There is a merging of different cracks whose summation is a kind of larger crack which travels faster and leads to a brittle failure. Okay, what else? We, of course, we deal with, well, this is again our spring. And what is very interesting is that at the beginning we were thinking that ceramic had no plastic behavior. That was the idea. Because and no plastic behaviors means that ceramics are brittle. So it's difficult to apply ceramic to make structures. Possibly you can make very small structures or very overweight structures. You can make a pot in ceramic because it has much more material than needed to withstand the forces. Or you can make some small structures in ceramic which are not loaded that much. You wouldn't make a spring in ceramic because it involves loading and unloading and so on. Okay, this is basically what you already know. And in what happened in the last 30 or 40 years is that we were starting to be involved into nanomaterials, into materials deformed at the nanoscale, even at the nanoscale. Applying this, for example, is silicon. Silicon is basically a ceramic, and you can see that at the nanoscale it deforms plastically, which you wouldn't see at the macro scale and even not at the micro scale. But at the nanoscale, you can have this kind of plastic deformation. This opened a number of considerations because then they were saying then we can make some tough ceramics. When I say tough, T-O-U-G-H, that means that the cracks are there, or one crack is there, but it doesn't move. You may have a pot in your kitchen, a bottle, a ceramic bottle, where you have a crack, which is there since 20 or 30 years, which is nice as an idea, but since they don't withstand tensile forces, the application of ceramics tends to be limited. And now there has been a research on ceramics which are able to withstand also some tensile and some flexural forces, also in a ductile and in a tough way, so without allowing crack to propagate. This means also other things, that you are able to rework ceramics. Now there is the possibility to mold ceramic, to mold the ceramic also in complex ways and also in different limited small dimensions and so on, which has a number of interests also in terms of biomedical applications and so on. So there is it's a field which is interesting to follow. Okay, compression tests instead. Compression tests are for concrete. Concrete, as you may remember, well, the difference between concrete and cement is that cement doesn't include, it's just a ceramic which doesn't include some fillers, which we call aggregates. In practice, cement, the problem with cement is that it tends to flow. In fact, is applied just as a junction between the two concrete parts of two bricks and so on. It tends to flow, over time, because you can imagine that there is also a kind of thermal fatigue. If I apply some cycles, which are not just loading and unloading, but if I apply some cycles which are hot and cold, or warm and cold, so for example, day and night cycle can allow the material to deform, to flow, because they are not elastic, not really elastic. They are viscoelastic. When I will carry on talking on that later on, but when you say visco, that means that viscose or viscoelastic, that means that it's sort of elastic, but it depends on time. Time has an influence. If a material is elastic, it's fully and really elastic. It doesn't make any difference if I pull it quickly or slowly. And usually I pull it quickly because I prefer to finish the test and work before as soon as I can. But in other cases, you cannot do like that. For example, with plastics, it makes a lot of a difference if I pull quickly or slowly, because they are elastic, or they are sort of elastic, but closer to viscoelastic. It's some time influence. When you say viscoelastic, that means that you have some time effect. Or you can have also viscoelastoplastic, which is even worse, because you may have a behavior which is in between elastic and plastic, which is what does it mean? That some parts recover completely and some other parts of the sample don't recover completely, but there is an effect of time. Anyway, when we are going to discuss about plastic, we are going to talk about this. Having said the difference between cement and concrete, the aggregates, which are sand, gravel, and so on, small stones, make the cement more stable because they have no fatigue, no thermal fatigue effect. Because the stone, of course, the stone gravel don't change dimension even in the cycles between day and night and so on. And so it makes them more stable. And of course, they don't suffer also the deformation due to the continuous application of a load on them. And this is called, of course, a composite, a ceramic matrix composite, because the matrix is a ceramic cement. Then you have this kind of cylinder or cube. You may have also a tube. And what you do, basically, you apply a force, a compression force, you squeeze it. At a certain point, it reaches the elastic limit. Then you measure the Young modulus. On concrete, there are more differences to measure the Young's modulus, because you usually start showing some deviation from linearity. Is less ideal than steel. It shows some deviation from linearity there, so you probably would need to stop somewhere linear to understand which is the intercept of your curve, which is the line you need to consider. Then you would have some you don't have a real necking, because what happens is that the effect of shear becomes evident and it starts to it's a different kind of necking. You wouldn't have necking on the middle side, but you would have some breakage on the extreme parts of the cylinder by shear, some part detaching and so on. Okay, so what happens with ceramics? Ceramics, you don't have any necking. You don't have any necking in most cases. So brittle fracture. So this is a recall, but don't apply. This doesn't apply to ceramics. This is a recall of how far you can go. So you have here the ductile tips, and you have a shear fracture, and here is the completely ductile. This would be like For rubber, you would get like that, not vulcanized rubber, not the tire rubber, thanks God, but the rubber, the kind of rubber like chewing gum or something like that. You get to a point. And what happens there is that, well, here you have the cup and cone again. I'm showing the cup and cone just to make it clear that what we were saying. Here, you know very well all this. Well, the numbers are indicative, but they are not far from reality. We have also some advanced ceramics. Ceramics is not just clay for the pots or for bricks and so on. We have also advanced ceramic like the ones for dental implants, like these dental crowns in zirconia, like these aluminium spheres, for example. And this is the typical behavior. You don't have any kind of plasticity. You have just elasticity, and you have a marked effect of porosity, a characteristic which is important in ceramics is that you have this effect of porosity because they tend to be porous, and porosity, pores mean that they can interact with cracks. When crack propagates into ceramics, it may interfere, it may go between some different pores, and in the end, it creates an effect of aggregation of the different pores and propagation, crack propagation. Crack propagation, so it's enhanced by porosity, which might be a problem if you want a structural ceramic. Here, alumina, for example, is used quite a lot as an abrasive, also as an additive in plastic for improve the abrasion, the wear properties. It's used also, for example, as a replacement, now no longer available. And for example, it's used also for cutting devices, for covering layers of cutting devices like silicon carbide and so on. The important thing with ceramic is also that it's difficult to have tensile measurements because really the deformation is very small, the strain is very small, and this means that sometimes it's not easy to measure the tensile modulus, Young's tensile modulus, and therefore it is preferable to have that flexural testing with some. How is obtained the flexural test? You have these beams, you have this flexural beam, this sample, and you have some pins which support the sample. What happens is that the engine is there, it pushes from there, and therefore the machine, the head of the machine moves, actioned by the engine, and it pushes until the sample it breaks. The sample is sustained by 3 or 4 pins. You may have 1 pin in here and 2 at the bottom. At a larger distance, you can have 1 at the middle between these two, the midpoint between these two, or you can have to make the load more even, you can have 2 pins at the top and 2 at the bottom, a 4-point flexural test, which is more usual for ceramic because it makes the load more constant, also the pressure more constant. Also because the deformation the tensile deformation you would expect is very low. The flexural deformation it's a bit more in a ceramic. So it's not a problem to measure the compression strength of a ceramic. It might be a problem to measure the tensile strength of the ceramic you measure usually that by the flexural tests, where, as you know, you have a compressed part and a tended part. Okay, I wouldn't go much further than this. I summarize the information we can get from the stress strain diagrams. So the stress is the ratio between the force and the sectional area, and is measured, the units are like a pressure. Please, again, don't be offended by that. We started, these are very simple things, but we need to be clear that we all know that, to talk a little bit further about materials and about material research. So strain is a pure number because it's it's the ratio between a gradient of an elongation and the elongation and the initial length, so the gradient of the variation of sample length and the initial length. And there is a proportionality, which is not obvious. On steel, we have an obvious proportionality, so it's not difficult to measure the Young's modulus. On ceramics, again, we have a proportionality. In some way, even if you need to have flexural test or compression test, but proportionality is there. On plastics, it's very difficult. On wood, it's very difficult. That explains why Leonardo wasn't able to discover that. Because there is not a real proportionality, because there is a mismatch between some the force you apply and what you get in your graph. So there is a kind of elastoplastic behavior and so on. But we are going to go into more detail later on. So the maximum stress you get is the material strength, which in some cases, as you may remember with steel, you may find out that the maximums you don't get to, you don't want to get to the maximum stress because the material is no longer elastic. It's plastic. It does, because you're simply rearranging in order to show necking. There is a phase in which the forces, the internal forces and internal structure is rearranging it in order to show necking later on. But you should stop before the elastic limit. It is important because you need to know which kind of load are you able to apply to your material. And sometimes it's not even sufficient, because with fatigue, if you want to apply that a million times, say if you have a bolt which is in a wheel in a car, and the wheel over the life of the car can turn millions times, you may need to stop well before that in order not to have fatigue effects. So we need to have a kind of over dimension of our materials, of our structure. Okay, so Young's modulus, which is often expressed in megapascal or even in gigapascal. In megapascal, even for many films and polymers, are megapascal is sufficient. In case of metals, you talk about gigapascal. For example, steel, it's around 200 gigapascal of Young's modulus. Aluminum is around 70 gigapascal. Anyway, Young's modulus is expressed as the material stiffness. So a material which is stiff has a higher Young's modulus. Okay, this was a little bit more theoretical than the previous one, because although it is connected with the kind of tests we make on materials, but the idea of this lecture was to start building a kind of specification of the materials, to try to understand how we get numbers out of our materials with different situations for different materials. As you may have realized, other materials are better tested in tensions. Some materials are better tested in tension, like steel. Others are better tested into compression, into bending. in the case of plastics, and we will see, we need to have an idea of the time and of the speed at which they are pulled, for example, in the side test. The speed is usually expressed in, say, millimeter per minute or millimeter per second, in the sense that the grip at the head of the machine that that moves together with the sample is actioned at a certain speed, which is what determines the elongation, the speed of elongation of the material. And the speed, the time of deformation can make differences. That's the reason why springs don't work very well with plastic. Plastic springs don't work very well. You have just some plastic springs in nylon. Nylon has little effect of time on its behavior, and we call the whole of the properties or how the material is characterized as the behavior, the material behavior. And other plastics, you cannot use really them to make springs because springs tend to require to have a continuous effect of up and down, say, think of the lift, for example, up and down, or of the car wheels, up and down in a repeatable way and cannot show any local plasticization, so cannot go up and down out of the axis. It's preferable they don't do that. So that's why plastic springs haven't been a great success, apart from nylon, which has a limited effect. Nylon springs, again, are small springs, are not very big ones. Anyway, you will have the next lecture on Friday, and for now, I will send you these slides. I will put it on my webpage. Please, again, feel free to send me messages by you don't find the materials or for other problems. In a few hours, I will have also the recording of this lecture, and I will equally put it on my web page on our website on Unicam. Thank you, and see you by WebEx on